Hi, welcome to me313 Mechanical Engineering Thermodynamics. The topic of today's video is the ideal Rankine vapor cycle, and the sections in the textbook are 10.1 to 10.2. Here are the learning outcomes. At the end of this, you will know the four principal steps that make up the Rankine cycle. You'll understand the relationship between condenser pressure and coolant temperature, and you'll be able to determine the thermal efficiency of the ideal Rankine cycle. So first I want to talk about what is the vapor Rankine cycle. And the vapor Rankine cycle traditionally uses water. However, it can also use things like refrigerants. And so this diagram I show over here, this picture actually, is a picture from Chino Hot Springs, which uses a Rankine cycle which works with refrigerant, which is a low temperature, or what's called a low quality working fluid, because it boils at a lower temperature. So here's what the Rankine cycle looks like. The ideal Rankine cycle has 4 steps, and the key is that that makes us different than, for example, like a Brayton power cycle, is that we have the working fluid is going through phase change. It's going from a liquid to a vapor to a liquid to a vapor, back and forth. So here are the 4 principal components. We have a boiler, and at this point, this is where heat goes into the system. And we take something that's pretty much a liquid and we turn it into a vapor. So you can kind of see in this diagram here going from blue into red. You can realize this is normally called a boiler because that's effectively what it's doing. It's taking something that's a liquid and turning it into a vapor. It's often a little superheated even after it becomes a saturated vapor up to a superheated vapor. And we'll talk about that here in a little bit. Then we run through a turbine. And this turbine is going to go ahead and generate some work as it goes ahead and spins. And what we do is that this material that comes through loses enthalpy. We know from an energy balance across turbines from basic thermodynamics. And then the material comes out usually as a vapor, but usually almost at a point where it's going to become saturated. Then the material goes into what's called a condenser. And this is where heat leaves the system, or heat leaves the cycle. So this is where Q out occurs. And effectively what we're doing is the opposite of the boiler. We're taking something that is a vapor and turning it into a liquid in the condenser. And then the final step is we take what is now a liquid, usually effectively a saturated liquid, and then we run it through a pump that's going to go ahead and raise the pressure. So there's a little bit of work input going in there, and the point of this is to raise the pressure. So we have over upstream of the pump a low pressure, and upstream of the pump we have a high pressure. Usually there's not much of a pressure drop through the boiler, and so we have this high pressure over on the other side. And then we run through the turbine and we come back down to the low pressure. So this cycle tends to operate between 2 different pressures, a high pressure and a low pressure, similar to the Rankine, or similar to the Brayton cycle. We can draw this cycle on a TS diagram, which is pretty useful. And so let's go ahead and do that now. The diagram over here on the left is labeled with some points. So what we'll go is we'll look at point 1 here. We'll just go ahead and go around the cycle. And point 1, as I said, is a liquid, and it tends to be a saturated liquid, so it tends to occur right on the left-hand side of this TS diagram. And I'll talk a little bit more about why that is always exactly a saturated liquid. Then we go and run through a pump, and if this is an ideal pump, meaning that it doesn't generate any entropy, on the TS diagram, we would go straight up to a point there. So this would be point 1, that right there would be point 2. So now we've got a little bit of compressed liquid, because you see the slope of this line goes to the right, but if it's an isentropic pump, it would go straight up. Then we go ahead and run through the boiler. So what it's going to do is it's going to go from a condensed liquid up to a saturated liquid. Then it's going to become boiled into the vapor. So it's going to come up to some point here. Then it's going to go ahead and move across. This is all within the boiler. And then often it becomes superheated as well. And so all the way up to there, and that would be point 3. So there's the second step. This is all going through the boiler. And then we run through a turbine. And so let's go ahead and for now assume that this is an isentropic turbine. So that this will now connect to point 4, which would be straight down on the TS diagram. Now, point 4 and point 1 are at the same pressure. So they've got to be connected by an isobar. Now remember, an isobar, which is a constant pressure, is also the constant temperature. So that would be a straight line there, and then a little bit of curve there. So this right over here, that line I've just drawn is an isobar. And in fact, this line up there is also an isobar, constant pressure. So that's the high pressure line and the low pressure line. So these lines are a little bit curved. There's a lot of little knees and disjunction each time that I run through the phase diagram. So we're going to look a little bit more in detail at this in just a little bit. So let's go ahead and look at the energy balances. And I say the energy balances because there's essentially a balance over all four of these components, and then we can do an energy balance around the entire cycle. So we'll take these one at a time. So let's go ahead and look at the pump here. As I said, we know pumps require work, so there's going to be some work that goes into the system. And what this does is it increases the enthalpy. So if I was to write my energy balance, I know that the work that goes in is going to be equal to the mass flow rate. So let's go ahead and do this on a rate time of H2 minus H1. And so that's the amount of work that goes into raising the enthalpy. It turns out that this is actually not require a whole lot of work. And the other thing is that we've got a compressed or a saturated liquid that's turning into compressed liquid, which is more or less incompressible. And so we can actually go ahead and approximate this enthalpy as just VDP, and this ends up becoming the mass flow rate times the specific volume, and this would be P2 minus P1. So you might remember that from basic thermodynamics as well. And so this is a little bit easier way to go ahead and determine what the work input is, and those are going to give you effectively the same value. Now the value of V, well, it doesn't matter which one you use because, as I say, it's incompressible. So usually I go ahead and just use V sub F at one of those pressures, and they're more or less the same, so with maybe a 1 or 2% change. So there's my energy balance using the pump. You can go ahead and use either equation, and you'll end up with effectively the same answer. Now let's go ahead and look at the boiler. The boiler's up here. This is going to go ahead and have some heat going in. Again, we'll just kind of talk about these all on a rate cycle. So if we write the energy balance there, the energy that's going in, Q in, is going to be equal to the mass flow rate. And now we're going to go ahead, and this is going to be H3 minus H2, which is the change in enthalpy. So there's the energy balance across the boiler. If we look at the turbine, turbine is generating some work that is going out. And so we look at that. It's going to be a similar energy balance that we just had for the pump. The work that goes out is going to be the mass flow rate, and simply H4 minus H3. And then finally, if we look at the condenser, which is where heat leaves the system, so we have Q going out of the system, and you can probably already figure out what that's going to be. Q out is equal to H4 minus H1. All right. So actually, I just realized that I miswrote this equation up here for the turbine. I've got this flipped backwards. Let me go ahead and fix that for you. If I want work out to be a positive value, I actually need to turn this around and make this H3 minus H4, because H3 is going to be greater than 4. The inlet enthalpy will be less than the outlet enthalpy. So as all of these, I've written these so that they're positive values: out minus in, 2 minus 1, 3 minus 2 is out minus in, and I should have done that over here as well to make this a positive value. The enthalpy is going up as we go from 1 to 2, 2 to 3, and then it's going down as I go 3 to 4 and 4 to 1. So that's why it's 2 minus 1 and then 3 minus 4 over here. It's a matter of sign convention. Now, W in, Q in, W out, and Q out will all be positive values. We can go ahead and determine the thermal efficiency of this entire cycle. Well, that's going to go ahead and be the desired over the required, which is going to end up being the net work over the heat that I put into the system. And the net work is going to be the work that goes out minus the work that goes in over the heat that I put in. And we can go ahead and range that to 1 minus Q out over Q in. And so any of those three forms will end up giving you what the thermal efficiency of this cycle is. All right, so I want to talk a little bit difference between what's called the ideal Rankine cycle and the real Rankine cycle. So a couple things about the ideal cycle. So let's go ahead and draw it over here. We start off with a saturated liquid that's at 0.1, and then we said that the ideal cycle, it would have an isentropic pump up to 0.2, and then we said that it follows an isobar as I move across like that. So that's all at a constant pressure to 0.3, and then we have an isentropic turbine 0.4, and then we have an isobar that moves across there. All right. So there's the ideal cycle. We have these vertical lines from 1 to 2 and 3 to 4, and we have isobars. I'll relabel that as isobars to remember that on the ideal cycle. Now, in real cycles, there's a couple things that are different. And so So let's just go back and look at our cycle here for a minute. Notice that we've got this pump that goes through a boiler, and then we've got a turbine that goes through a condenser. And there's a lot of piping in here, and so you can actually have some pressure drops. So actually, sometimes there's pressure drops between 2 and 3 and 4 and 1. So if we come back to the diagram over here, and if I was to look at, draw this on a real cycle now, I'm going to go ahead and start at point 1, and I've got some point 2 right there. If this is, actually let's do this in a, I'll draw it in red there, and I'll change that pen color. If that right there would be an isobar, in actuality there might be some sort of pressure drop. I'm going to give myself a green pen, and so it would actually kind of drop down to lower pressures, and it might be at that point there, which would be representative of the pressure drop through the boiler as I move through there. Then if I was to come down through my turbine to that point, and again, if this was to be an isobar that moves through, and I was to think about what would happen if I had a pressure drop, well, I've got to come back down to this pressure, so I actually would have to have this start off at some higher pressure. So I would have pressures that go down as I move through the system, going in this direction and that direction. In this class, we really won't worry too much about pressure drops because you need to be solving the fluid dynamics of it. We want to go ahead and focus on the thermodynamics, but it's good to recognize what is different between the ideal and the real. And another thing is that, as we just mentioned with the ideal, these are vertical. You could have an efficiency where these would actually be sloped up and to the right, and then this might go down and to the right. And so in the ideal cycle, we go ahead and have those tilted. And this we can go ahead and calculate. This would be for the isentropic efficiencies of pumps and turbines. So that we can actually solve for in the realm of thermodynamics. I want to mention a little bit about condensers because I keep mentioning how the outlet on the TS diagram is a saturated liquid, and I want to mention why that is. And so it's good to look at what a condenser looks like. So on the right here I show a condenser, and it's actually all you really see is the outside shell of the condenser. And so on the left is a diagram of the inside. And so the light blue is cooling water. And so this is actually not part of the cycle. This is what's cooling off. And so what's coming in here, this would be coming from point 3, and this is a superheated vapor, but just slightly superheated. It's just coming from the turbine outlet when it comes into the condenser. So that's the turbine outlet. It's slightly superheated. The vapor comes in, and it hits these cold pipes. And these pipes are kept cold by running a coolant. And again, this is not part of the working fluid. This is, for example, taken out of a lake or out of a river somewhere. And water is pumped through this series of pipes. And what we're trying to do is create a lot of surface area so we can get a lot of area for cooling. The vapor comes down, and then it quickly hits these cold pipes, turns into a liquid, and we lose all that heat, and then that liquid dribbles down. And so what ends up coming out of here is going to be a liquid, but you can realize since it's liquid in equilibrium with its vapor, this is end up going to be a saturated liquid that is coming out of this system here. And that saturated liquid, well, effectively it's going to be at the same temperature that cooling water. So it's going to be whatever T of the coolant is, right? It's going to end up being Psat at that temperature right there. So there's a relationship between Psat, which is actually P low, and what the coolant temperature is. If I run cooler water through, I'm actually able to lower the pressure that I'm running. So this would be the low pressure of my Rankine cycle. Let me go ahead and kind of just show this in the diagram a little bit. Let me erase some of the stuff I just wrote and come back to my pen. And so if you remember on our cycle we had this isobar that was at a point right there. So this would be going, this is the condenser. So it's going from point 4 to point 1, and that's an isobar. Right? And it's occurring at this temperature. And so this would be, for example, the temperature of the coolant. Now, if I was to run colder water through it, I would end up dropping that down to some lower pressure, and I would actually be at a lower pressure and a lower temperature. So the temperature of the cooling water actually controls what the low pressure of my cycle is. And if you remember on the TS diagram, the net amount of work is the area in this curve. Then we'll sketch up the rest of this diagram, right? So that's the net work. So notice that if I was to go ahead and drop the temperature, I'm pulling this line down. I'm actually generating more work from my system. So I end up with something that's more efficient. So it's good to use a colder water. So actually, power plants tend to work a little bit better in the winter when their cooling water is often a little bit colder. And so using water out of China's river, for example, which is right at freezing in the winter, is more efficient than we're running it in the summer. Anyway, so there's the reason why the temperature of the cooling water controls the low pressure, and that's the reason why this outlet is effectively always pinned to the left here as a saturated liquid, because that's what's dribbling out of here. It really doesn't become a condensed liquid, because as soon as it condenses, it tends to just drop off those pipes and dribble out of the system. So it's kind of a consequence of the way that the condenser looks. So back to my diagram over here, there's where that superheated vapor is coming in. This is the cooling water coming in that side and coming out over here, as you see right there, right over there. This diagram isn't exactly the same, but it's pretty close. So it's just kind of running over the ends of these cooling water pipes and moves through. So there's a big flange there. That is that flange right there. All right, so let's do an example problem. We're going to work with the ideal Rankine cycle. So we have steam that's entering this turbine at 350 degrees Celsius and 3 megapascals. So that's this point right here, 350 degrees Celsius and 3 megapascals. And let's go ahead and just sketch up our diagram fairly quickly on the TS diagram. This would be point 1, point 2, point 3, and that right there would be point 4. And I'll go ahead and drop my isobar at that point right there. Okay. And so a couple steps that we're going to have. We've got this point completely specified. So we know where point 3 is. We know point 4 is straight down from point 3. We know point 1 is pinned over at this lower pressure right there. And that, we're also told, is at 75 kPa. Okay, so that temperature is going to be the saturation temperature at 75 kPa. Point 2 is straight up from point 1, and it's at 3 megapascals. So that kind of completely specifies it. Let's go ahead and find out what Q in and Q out is, and just kind of remember this is where Q out is, this is where Q in is, and we're not given a mass flow rate, so we're going to do everything on a per mass basis. So we involve a lot of looking up values in tables and interpolation, so this is going to be a lot easier to do in EES. So I'm going to go ahead and do this in EES. And I'm going to do something a little different than I did before. I'm not going to type it out, because I think typing on the computer gets kind of loud and annoying. And so I've actually already got it written out here, but what I'm going to do is spend a little bit of time explaining what I have on here in terms of the EES, and then we'll solve it. So let me just first mention this top line I have, where I have this $sign in the word unit system. This is a specification where I'm just telling EES what unit system I'm using. And this is the same way if I was to go up under options and set my unit system right here manually. But if I type it in here, I know by looking what unit system I'm using. And so I'm saying I'm using the SI system, and then I'm also specifying that it's degrees Celsius, kilopascals, and kilojoules. And that tends to be the default. So if you just open up EES, these are your default units. But here I put it on so we clearly know what unit system we're using by looking at it. So this is sort of optional, but kind of helpful to you if you close that window. So the first thing I give is what's specified. And the points were specified at point 3, and the temperature and pressure. So 350 and 3000. I know my units. I can just glance up here, so I know what my units are on there. And the low pressure, which was at P4, and the condenser was 75. So those are the 3 things that were given in the problem. Then I'm doing isobaric steps. And I know that the pressures in the ideal cycle are the same. So P1 is P4, and then P2 is P3. And so I've now actually got all of my pressures. 1, 2, 3, and 4 are completely specified. So I have one intensive variable at all states. And now we're going to go ahead and look at a couple other things that are true of the ideal cycle. As we mentioned, the condenser outlet is a saturated liquid. So that would be the quality at point 1 is going to be 0. So I specify quality at 0. And then I've got my isentropic pump. So I'm going straight up on that TS diagram. So first I find my entropy. I know X1 and P1, so those are my 2 independent intensive variables. So I'm going to say the entropy at 1 is of water, and I give it P and X. Those are 2 independent intensive variables. And then I go straight up, so I say S2 is equal to S1. And so now I've got the entropy at point 2. I know the pressure at point 2. So again, I've got 2 intensive variables that are independent at point 2. So we're kind of moving around the cycle. So let's go ahead and point 3 was already specified in the problem, T and P, which are independent. It's a superheated vapor, so we can go straight to point 4. So I've got an isentropic turbine, same way I do the pump. I specify what the entropy is. Here my 2 variables are P and T, P3 and T3. and then I'm going to say S4 is S3. It goes straight down on the TS diagram. And now I've got S4 and P4. So what I actually have now is two intensive variables at all the states. And so actually if I solve this and look at my array diagram, and let me expand this out a little bit, I can go ahead and see that I've got P and S at all four states. So I have two intensive variables. So everything's been specified. And so then I can go ahead and just quickly, since I know P and S at every one, here's what I just duplicate. I'm going to just find the enthalpy at each point using the P and S pair. And I can use any two. I could have done, like for point 1, I could have used P and X as well, but this way I can go ahead and solve for all four just fairly quickly. So I duplicate the variable counter I'm using it I. You can use any variable name in there that you want. And now I've got the enthalpy, so we go back to those energy balances to find in all the steps. And so I'm going to use my efficiency as 1 minus Q out over Q in, this last sentence. So Q in is 3 minus 2. Okay, that's in the boiler. The condenser is 4 minus 1. Excuse me. And so then I can go ahead and find out what the efficiency is, which I'm calling EFF for the efficiency. And now if we go ahead and solve this, as I've already done, we've got Q in and Q out. That's going to end up being in kilojoules per kilogram. And here's my efficiency at 26%. Couple things I want to point out as well is that 26% isn't particularly high. If you remember, our Brayton cycles were a lot higher. And so this is actually, even this is an ideal cycle because we're not using any reheating or regeneration, which we're going to talk about in subsequent lectures. Our efficiencies don't tend to be all that high for a typical Rankine cycle. But we'll see ways that we can go ahead and improve that and get efficiencies that are close to what the Brayton cycle is. Alrighty, well, that wraps up for this video.